back to the big overall picture of regularizing moduli spaces of pseudoholomorphic curves. The one piece in the geometric realization story that I owe you is a very sort of high-level sketch of how one gets equivariant transversality. And then that makes sense because then I can also ask guiding questions about equivariant transversality and then also guiding questions for abstract regularization approaches, and then we can go into the abstract ones. And the one thing where I'm going to make my life easier is, I'm not going to ask guiding questions about isotropy or gluing. So everything that we'll be worried about will be more basic than isotropy or gluing. And that's the reason why I sort of did discuss non-transverse gluing a little bit, so you have some idea of what one can do there. And I'm also going to say a little bit about what one does with finite stabilizers. So that's just going to be a recipe that says, if you understand the story without stabilizers, this is what you need to do to get a story with isotropy. And that's going to be very, very high level. But essentially my mantra is that we've understood isotropy and orbifolds. We've understood the hard part in gluing. So we've understood the hard topology and the hard analysis that are straight in our face. There are more basic questions that we, I think, forgot to look at. So that makes them more interesting. So getting us grounded again, my main example for now, I've disposed of gluing. So I'm now going to look at a homology class in which bubbling is excluded. So that when I look at these genus 0 curves with one marked point that I'm fixing infinity, that has a chance of being compact. So that will be my running example. Incidentally, that's also directly going to mean that the isotropy is trivial. So this will actually stay our main example. And again, what do I actually want? And what is the language for that? So seeing sort of language confusions. So the example that I did in the geometric case is I actually made a smooth structure on the compactified space, possibly after perturbing J. So it sort of regularized it into something that's a smooth manifold in that case, but it was unique only up to cobordism. And when there is isotropy in the geometric world, you would expect orbifolds. And it will turn out that in the abstract world, we're not going to really see orbifolds, but weighted branched manifolds. But that's not so bad because you can turn orbifolds into weighted branched manifolds. And all of those have some kind of fundamental class. It's just that that's going to be a fundamental class with Q coefficients. Whereas, when we have manifolds, we expect, well, if we have oriented manifolds, we expect, fundamental class with Z coefficients. So, yes, question.
How do you see that isotropy is necessarily trivial in the first example?
You talk to Dusa for a little, and she'll convince you.
Okay. So
you talk. Well, so let's see. So the only way that you can have non-trivial isotropy is by having multiple covers, and somehow, once you have multiple covers in a homology class,
or you can decompose your homology class to the sum of two non-trivial things.
Right, and that actually happens as a bubble somehow. So if you go into this and you take sort of 2 times the basic class, then you can take the sphere that covers that basic class once, and sort of take a nodal sphere and kind of see that as the limit of some parametrization of a multiple cover. So it's kind of a silly bubbling. It's not one that you see geometrically in the image, but it happens in the description of the moduli space. Good. Right. And since we're asking Dusa, this is a neat little paper by Dusa McDuff. And I believe there's also an observation that may be due to Dusa or Joyce that says you cannot necessarily turn every weighted branched manifold into an orbit fold, I believe. So this is not quite the same. But this is the way that you get fundamental classes of orbit folds. So not so bad. Right. And I want to give these names because we've seen a lot of sort of words that say fundamental cycle, fundamental class, virtual fundamental class. So I'd like to keep these apart. If you actually have a manifold, that's a cycle. So I would call this here the fundamental cycle. Possibly virtual, if for some reason you feel that that's a shaky thing, or that the cobordism class here means that that's not like a cycle, but it's a cycle up to something. This here will be a straight-on homology class in some kind of homology of this compactified space. So I don't see any reason why I would call that virtual. I would call this the fundamental class. And in fact, what people have really sort of called more sort of virtual fundamental class is a construction that somehow doesn't really care about making the fundamental class, but it just cares about defining its push forward under some good maps. Right? So the basic example is the evaluation map of our basic space of holomorphic spheres. That's a nice continuous map. So if there's a fundamental class here, of course you could push it forward. And the word virtual here refers to not actually defining M bar by itself, but just defining its push forward. So that's the official meaning, I believe, of virtual. So in the same sense, you might want to talk about virtual cobordism class if you're not talking about the cobordism class of these manifolds, but you're talking about the cobordism class of these cycles, right? Maps from the regularized space to N. If that's a smooth manifold, then that map is a cycle. It's unique up to cobordism. Right, so that's already pretty close to a class. So, ways of keeping sort of our goals apart a little. However, I don't actually know of any approach that very clearly cannot achieve both of the first two, and only achieves the last somehow. If you really look at the papers, I believe they actually all construct the first two. They might not say it that way. All right, so that's our goal. And so here was the program in two different approaches, depending on whether you want to think of your compactified moduli space as this quotient with glued on stuff, or just as the zero set of something. So, the transversality part, it happens in very different places in these two. Right? In the abstract place, you do a whole lot of setup, and at the very end, you're finding some perturbation so that your perturbed section is transverse to zero. And more, uniqueness. And that sort of abstractly comes out of whatever abstract regularization theorem there is, and that allows you to then replace M bar by the perturbed zero set, and that is your regularized moduli space. Which then makes sense as a cobordism class. And I think in the very beginning I explained a little bit of how, when you let nu go to zero, you can actually get a check homology class in the actual homology of the unperturbed space. So that then is the end of the story. So really the hard part is getting this whole description and getting some meaning in which those are sections. So whereas in the geometric regularization world, really getting this transversality to be global and equivariant is the hard part of the story. So, the Fredholm, the section description here is just on the level of d bar j here, and there's a quotient and gluing afterwards. So what we want in terms of equivariant transversality, usually, right? So we're thinking of perturbing the j. So you find a j prime so that the perturbed d bar operator is transverse to zero. And, because you want to quotient afterwards, you still need the perturbed zero set to have an action of the automorphism group. That's what we mean by equivariant transversality. And not only that, so you then sort of reproduce this bit. You would then also like to say that somehow, although you've perturbed from a sort of far away point, I've just added some perturbation to my PDE. That perturbation was equivariant. Good. But also after perturbing, somehow my solution space should still have the same kind of compactness properties that it had before. In our case, that is not really surprising because we have Gromov compactness, and that doesn't care about which J you use. But sort of on a more abstract level, you'd better make sure that there's. So you can take the perturbed zero set. If you had equivariant transversality, you can quotient by out. But you need sort of a new gluing for the perturbation, and a new, somehow, extra set of broken things that somehow have something to do with the perturbation. So that the same kind of construction is again going to give you a compact space. by Gromov compactness, if we're wiggling J, that is not terribly surprising. But, you know, in general, no good reason why that should work. And in general also, you know, you've got some magic. So now the next magic is that I should have this answer to be, you know, independent of J. So if I have J double prime, that's not J prime, then I'd like to find cobordism between the compact moduli spaces. Right. And then this is my cobordism class of regularized spaces. So that's the cobordism story. Right. And here I've really sort of gone away from a wording even where there was boundary. Right? If there's boundary, you might want sort of relative fundamental cycles. But anyways, let me just spell this out by magic. There we go. Awesome tricks of a smartboard, right? So if this had been a theory with boundaries, then that also means we're not just defining counts, really we're defining some kind of algebraic structure, and then the boundaries give us you know, the algebraic axioms. And so, yeah, then also, yeah, as in Fleur theory, it's not sort of the counts that define the differential that are well defined, it's the homology. And so to prove that the homology is well defined, that's this sort of buzzword continuation maps. The continuation maps here in this example are the chain maps that you find, you know, by varying J, you know, from one complex to the other and back. And then the third step of this whole theory is that you better prove that these are inverse to each other, so you actually have an isomorphism or homology. So you need to not only find the chain maps, but also chain homotopy equivalences. So that was the complaint that, you know, once you've done this in Fleur theory, you have to do it twice more. Question.
Can I make sure I understand what you mean when you say equivariant transversality?
Yes, please.
So does it mean that you have a bundle E over B,
Mm-hmm.
you have a group action on both spaces with the action on the top covering the one on the bottom?
Right.
You have an equivariant section, and you want to find an equivariant perturbation nu, so
right.
that after you apply that, you have transversality.
Exactly. Right. Right. So, yeah, in this world, you know, the new section here is d bar j prime, and I want that to still be equivariant. Which means, you know, in this world here, if I sort of write this as, if I wrote d bar j prime, I could write this as d bar j plus perturbation, right? And then what I really mean here is I need that to be transverse to 0, and I need somehow, if I act first with an automorphism on nu, that should be the same thing as first acting with nu and then acting with the automorphism. 4, 5. And I'll write this out in more glorious detail when we get to the nitty-gritty of getting the transversality equivariant. There will be some meta discussion of what this equivariance does to you in the Sard-Smale theorem.
Do you still want a counterexample in the bidimensional case?
At some point. Yes, please. Good. So, how do we do this, right? So how do we find, this equivariant perturbation? So, yeah. Right? So, I'm going to try to do this in total sort of general formulation here. So, we need an appropriate space of perturbations of our differential equations that are equivariant. So, for example, right, if I write P, really here I'm going to think of this as adding something to my section. So in the world of J's, this is the difference between D-bar operators. So where J prime is another admissible almost complex structure. And right, so I'm thinking of nu as taking S to S plus nu. Or D bar J, I guess. Let's do that. And the equivariance is what I wrote, I guess, on the last slide. So for all phi, I should have nu commute with the action of phi. So then the approach, this is not the only way of finding equivariant perturbations. It's the way that has been used, and I don't know of any other way. So you have a good universe of perturbations that you can play with, and then you look at the universal moduli space, which is slogan for taking the pairs of perturbations and then solutions of the perturbed equation. So if you take the space of all J's, this is awfully big because you're somehow taking a union over all moduli spaces for all J's. So this is massive. We'd still like to get this one cut out transversely. So the map that takes not just u to d bar u, but u comma p to d bar plus p. Right, nu is equal to p here on u. In whatever bundle I live, I want that to be transverse to 0. So very symbolically, I can write the differential of that. So, varying u in xi direction, varying little p in capital P direction. What I should see, right? So first, I just linearize the d-bar operator. That's this guy on xi, and then the p of u varies in two different directions, namely in the u direction and in the p direction. So I have a dp applied on xi, and then the variation capital P on u. Well, I guess here I'm sort of thinking of the P as, oh no, this is in the tangent space. Yeah, this is very symbolic notation, right? So this looks weird because there are three components, and we're usually just used to having two. The solution to that puzzle is that this two together here is actually, if you're at P that corresponds to J prime, then this is the linearized operator of D bar J prime here. So we should not really worry about this middle thing. And in more abstract version, let me just think about this at p equal to 0. Right, so then that here doesn't exist because it's the linearization of a map that is 0. So that's gone. And there will be a friendly Fredholm lemma that will allow us to not necessarily have to prove. Oh, I didn't say what this means, right? So transversality means I need, well, we're usually used to saying surjectivity, so I can get an implicit function theorem. But this is going to be in infinite dimensions, so we actually need a right inverse. And we need a right inverse at all solutions. That means this space is cut out transversely. Okay, and the Fredholm lemma is going to allow us to only prove that this map has dense image. So, and dense image then means all I need to check is if I have something that's perpendicular to the image, then it better be 0. So, meaning if I have a non-zero element that's perpendicular to the image of the d-bar operator that I actually care about, then it can't also be perpendicular to these p's. So there's some inner product happening so that I'd like to get this non-zero. Right, so I'm proving that the perp to the image of this is 0 by assuming that there's an eta that's perp to that and non-zero, and then I prove that it can't, that, right, this pairing with eta is not always 0 for all p's because I find a p for which that's non-zero. Phew. And this is the important piece that we're going to need to think about whether we can actually achieve that. So, there's, of course, when you read papers, there's sort of a lengthy story and a whole like new Fredholm setup, and you talk about the universal moduli space. But if you want to sort of zero in on the place where the important work happens, this is the one. Because the rest then is always quoting the same kind of thing. So, right. So if we have this transversely cut out, then we can quote the implicit function theorem for Fredholm sections in Banach manifolds that say this is actually a Banach manifold, my universal moduli space. And then I can look at the silly projection from my Banach manifold from the pairs UP that just remembers what the perturbations were. So I want that Fredholm and Banach manifolds. Then, well, in infinite dimensions, regular values are still dense, but only under a condition that connects the differentiability with the index of this projection. So, and then the regular values in that world are, just write that out here. So those are the images, right? So the perturbations. So that for all pre-images, the differential is surjective. So pre-images are elements U that are, in the P fiber of the universal moduli space, and I'd like this differential to be onto and the official phrasing of the Sard-Smale theorem is that the regular values are actually comeager, and that's a notion in metric spaces that implies density. So, in complete metric spaces that implies density. So now we need to ask ourselves a couple of questions. First is, was this thing actually cut out by a Fredholm section? So that better be transverse and Fredholm, so we can quote the implicit function theorem. No, hold on. That was silly. That was wrong. Of course, it's not a Fredholm operator because it does not cut out a finite dimensional manifold. Right. The thing I need to worry about is whether this is Fredholm, that projection. And I also need to worry whether I can get the right differentiability. And then I need to worry whether these regular values are actually ones that give me, regular J, so transverse equivariant perturbations, because this is just about the projection. So that's where some funny linear algebra turned in infinite dimensions helps us. So just this is a general fact about Fredholm sections plus bounded linear operators, but I've just written it in terms of the linearized operator and what we have here. So our linearized operator is a Fredholm map now, right, between Banach spaces. And the thing that we're adding to it is this map that takes a perturbation, a tangent vector to the perturbations, and sort of evaluates it on U. That's why I've called it E sub U. We'd better make sure that that's a bounded linear operator. And what I checked up here is that its image is dense. So that's the red box. So then this lemma tells us that it actually has a right inverse, which means we can run the implicit function theorem here. And more, it tells us that the projection of the kernel to this tangent space is Fredholm. So the kernel of this sum here is now exactly, right, that's the kernel of this operator, which was the linearized operator for the thing that cuts out the universal moduli space. So that means this kernel here is nothing but the tangent space to universal moduli space. And this capital pi here is nothing else but the linearization of my little pi. So Fredholm lemma tells us that that is Fredholm. And that's exactly the meaning of what I mean when I say that some nonlinear map is Fredholm. I'm saying all its linearizations are Fredholm. So we're good here. And not only is it Fredholm, the claim is that its index is equal to the index of the first Fredholm operator. So that is, right, the index of, this is capital pi, this is little d pi. So that tells us in which indices of the d bar operator we can run this. So we can satisfy this by making sure that this index here is less or equal to k minus 1. That's something we should make sure is true. And not only are the indices of these two things the same, we can actually identify their kernels and their co-kernels. And what we're interested in is the identification of the co-kernels. So that's the quotient of the target space by the image. So in particular, capital Pi is surjective if and only if the linearized D-bar operator is surjective. So this statement here in the set of regular values is the same thing as saying the linearized D-bar operator is onto, except now at the point d bar j plus p. So, yeah, regular values of a projection are turned via this Fredholm lemma into actually, regular perturbations of my operator. That might be completely natural for some, and for others get confused every time. You look at this universal moduli space and you ask yourself, well, why do regular values actually mean anything for my actual problem? And the answer is this Fredholm fact. Right. So, that question.
What is K?
Well, K is right. So that means as you now set up your whole Fredholm description, right? You'd like to So this universal moduli space here will start with sort of maps of a certain Sobolev space. WLP maps. And now you get to ask yourself whether WLP maps are actually a smooth Banach manifold, or maybe just a CK Banach manifold. And I think they're just CK Banach manifolds where K is a little bit smaller than L. So you need the Sobolev space to embed into CK maps.
So once we know what indices we care about, we can still choose K to be bigger than that.
Right.
That's
that's what you need to kind of do here. And that's a little bit subtle, right? So that means you can't. Unless you can find a way of sort of describing your universal moduli space as cut out from a smooth Fredholm section, you get some limitation here on the indices in which you can get regularity. Which again is not so bad, because we're not just going to get dense sets, we're going to get co-meager sets. Right? And so then you could run the same kind of arguments with larger and larger degrees of differentiability here by using smaller Sobolev spaces, right? And hopefully the same space of p's. And then you get, as you then you're able to let K go to infinity, you get some countable intersection of co-meager sets. The intersection will be co-meager again, and so you get density, and then for all indices, transversality. But it is a little bit dicey. So it's a good thing to keep in mind there. Right. So, right. Upshot is, we can forget about the Sard-Smale theorem, we can forget about the Fredholm lemma, and just make sure we get the right kind of starting set of perturbations, right? Make the kind of differentiability that we need, and then check our, density of the image of the universal linearized operator. So. This is the time where I'm going to get very philosophical and try to translate what it means to actually have equivariance. So, and I want to think about a case where my perturbations are kind of differential operators. There are other ideas. So I'm going to think of what, the analyst would call these local perturbations, which means they come from perturbations that are somehow maps maybe from my base Riemann surface times my symplectic manifold to whatever it needs. So, yeah, it's a perturbation to the d-bar operator, which means when I then write P of u, right, that should be some kind of perturbation to the d-bar operator, so it should be maybe some 0-1 form on the surface with values in q star Tm. So that means it needs to have a value at each z. And so the locality is that at z, the value should only depend on, well, I allow z here, but not on all of the map u, but just on its value at the point z. Well, that's a zeroth order differential operator. I could also allow it to depend on the derivatives of u at the point z. But my d-bar operator is a first order operator, and so it kind of makes sense to try and just perturb with zeroth order operators, because those are, you know, compact perturbations, and so we have some chance of at least preserving the Fredholm property. So I'm just going to write it this way. Right. And now the action of the automorphism group is more precisely saying that I need, well, P of the reparameterized phi to be P of u acted on as if this was the d-bar operator of u composed with phi. And the d-bar operator is just changed by composition with d phi. So this is what I'd like. Right, and now right, so this automorphism group, yeah, those are maps from the surface to the surface that, you know, preserve I. So in this local world, what this means at every z is that I have P at, this is P at z at the point u of phi of z. And this here, on the other hand, is P of whatever I get out of the d phi here. But that, you know, applies phi to z first before I apply P. So there's a phi of z here, and then u of phi of z. Question?
So aren't our perturbations first order?
Ooh, boy. Yes, damn, sorry. Right, because, oh goodness, yes, the difference between two d-bar operators for different j's. Goodness, right. Yes, good bullshit detection. Right, so d bar j minus d bar j prime is in fact first order. So note, right, we are perturbing a Fredholm operator by a first order operator by a first order operator. So it's not even clear that we're preserving the Fredholm property or compactness or anything. That's all comes from, you know, specific theory for d-bar operators. Indeed. And so I should write here u prime of z also. But then, right, all that I do here is I should have u prime. Well, I should. This will depend on derivatives of u composed with phi at z. But that's the same thing here. So because of the chain rule, so this will be du composed with d phi. So I shouldn't make this. This is not red. This is green. This is not. Oops. this is not a problem. So these terms are in fact equal to those terms. The problem is in needing to make P of z comma something equal to P of phi of z comma something. So the upshot of this very abstract argument is that if we want local equivariant perturbations, then they'd better be, their dependence on the base space must be sort of invariant along the orbits of these reparameterizations. An orbit of the automorphism group, now I want to think of it not as reparameterizing, but as actually mapping z sigma to sigma. So this is sort of the points phi of z where I run with phi through my whole automorphism group. So this would be out acting on a point z in sigma. These are all subsets of my surface. Okay. And this is, well, looks pretty obscure. The two examples you should have in mind is R as automorphism root acting on the cylinder. Right? Then what happens here is, I pick a point on the cylinder, I let R move, act on it, I get a line. So those are my orbits. Or, right, in our base example, we wanted Möbius transformations that fix infinity, so those are just linear transformations acting on P1. Well, okay. There are two types of orbits here. If you move infinity around, you don't move infinity around, so that's just a point. But if I start with any other point, I can move it wherever I want in P1. So this really just has one orbit, which is pretty much all of P1. So those are slightly different. I want to sort of more think about the cylinder case. And think of splitting the surface into out orbits and a complement. So the example here is mainly the cylinder being R times S1. Right, so where all the R's are the orbits, and this one is this extra parameter. And so if in that sense I look at a point, that has parameters S and T, then I should have P of Z and U of Z just equal, it's only allowed to depend on the second parameter, P of T. However, this does depend on the first parameter via U. So that's...
It's not necessary to have like a local slice for R, is it?
No, well, it always has a local slice.
Global local slice.
Yeah, no, it's not necessary. I mean, this is, and this is sort of meta arguments here anyways. So, the upshot is, right, in Floer theory for the cylinder, that tells you that the mu J, so you're allowed to let J depend on the S1 parameter but not on R, simply because you want symmetry in the R direction. Right? A little bit more non-trivially, right, in our case of holomorphic spheres, we do want to quotient out by these reparameterizations. And, you know, because we need that symmetry, we're now not allowed to let our J vary with, you know, along the orbit. And so J is only allowed to, you know, is not allowed to depend on the base point in P1. So that's essentially, you know, the point that I want to make here, right? Whereas if you looked at sort of parameterized holomorphic curves, you know, maybe because you have some marked points, or you know, you have a stable domain, so you don't actually have to quotient by automorphisms, right? Then there are no real orbits to think of, and then the splitting here is trivial in the first factor, so then the surface is this whole T. And so then your perturbation is allowed, or your new J is allowed to vary along your whole surface. So
you could look at a stable domain where you have non-trivial but finite stabilized.
Finite stabilized, right. And that's yes, and then you can get into the world of multi-valued perturbations. So in that world, I would say still I allow my perturbations to depend on the base point. And then I'm just going to have to deal with this sort of finite symmetry groups that I screwed up. So, yeah. Right. So the point here is to say, depending on what symmetry you have, you're sort of more restricted in terms of what kind of perturbations you can choose. Obviously, right? But what that means is this dependence there. So, all right. And now I should make sure that, you know, even my space of perturbations has some sort of, you know, Banach manifold structure that's CK differentiable. And do that one way or the other. So I think what we said before is that one way of making sure this works is that, you know, you talk about maybe Sobolev space is WK plus 1P and take P bigger than 2, because then these maps will automatically be CK, and those maps will somehow, you know, enter in the transition maps of the Banach manifold B. So, and right, P we might try to do something similar. So usually you would take P to be coming from the almost complex structures in a maybe CK closure. All right. Good. So then we're just still dealing with this index restriction, right, depending on what K shows. But mainly we need this dense image now. So that's going to be fun to try and abstractly argue how we do that. So let's see. Right, this is sort of a very highbrow, somehow generalized discussion of what I did do last semester for the example of Gromov non-squeezing. So first thing is writing this perpendicular to differential operators. You can, in an L2 perpendicular world, that's kind of a weak differential equation, and that weak differential equation is in some sense there's this some adjoint operator on eta that's 0. And then, well, that's that's the right kind of operator here, that should satisfy some elliptic regularity, and you can see that eta, well, ideally we'd like eta to be smooth. More to the point, I need it to really be C0, because I would like to find a point now at which it is non-zero. And then I'm going to find that, I'm going to use that point to make this right-hand side non-zero. So for that purpose, I should rewrite that right-hand side and partition my universe into what I want and what I have. So what I want is, I want this integral here, so L2 inner product, to be non-zero. And this is where the local form of, I'm just going to keep writing u of z, where really I mean the germ. Where the local form of the perturbation comes in. So I'm going to integrate this dz. Now I want to think of this in this splitting of my surface. So, for spheres, this is a silly splitting. This is essentially, this is just integrating over the point here. But for cylinders, I'm integrating over S1. That's the complement to the orbits. And then I have a product on the orbit. That will be some L2 thing on the orbit. dt. Okay. So the reason I write it this way is that you can see this P is allowed to depend on T. So I can use in here p's of the form cutoff in T times some P0. And then I just need this interior thing to be non-zero, at P0 for some fixed time. And then near that time it will also be non-zero with the same sign, and then I can cut it off near T. So that means in order to, now I really need to just make this interior thing non-zero for some T. So, well, there are these points in particular. So now my first goal here will be to find one of them at which eta is non-zero, and a P organist. So it's multiple layers of notation. See, I want this to still be P at T0, comma something. So I just need to find that one perturbation at this fixed T, so that this interior thing is non-zero. That at T0 to be, well, non-zero. Right, and then the claim is, well, that's what I just explained. So then, you can cut it off. You get this non-zero. But how do I do this? Right. So I'm going to do this again by trying to make this equal to a cutoff function times some p0. And step 1 of finding this particular perturbation is to find p0 so that, I guess, and S0 also, so the point where I have non-trivial things, right? So my eta is non-zero at some point, and you'd hope that I'm at least allowing perturbations that, at a fixed point, can vary enough so that I can pair it with any kind of vector at that point and get something non-zero. I'm going to be picky here and make it bigger than 0. So that's a basic, restriction on the space of perturbation sort of locally being free. Well, now eta was smooth, so this tells me as long as I take S near S0, I have the same thing also be positive. And now I'd like to cut off near S0. But the problem is, let's see, like this. So if I try beta times p0, what does this actually look like? It's an integral eta of s p0 times my cutoff function that should be of the allowable form p. So p is allowed to depend on t and not on s. So t0 is fixed here, so the only thing that beta is allowed to depend on is the point u. So I'm not allowed to let beta depend on s because that would break my automorphism symmetry. And so I would like this cutoff here to be supported near s equal to s0, so that I could deduce that, well, that pairing is always positive, and so the integral is positive. But, it's a function on M. So, well, I'm going to make it supported near u of S0, T0. Well, and now I'd better make sure that a point u of st being close to this implies that s is close to S0. So that looks like, almost injectivity, what we need here. So what I need here is I need to find, I need to find one of the T0s. I'm allowed to play with those, right? So in the cylinder case in flow theory, I'm allowed to fix one parameter on the S1. So I just need, and then I need somewhere injectivity along one of the R rays. And essentially, once I have injectivity in that sense, I get sort of this more quantitative injectivity also. There's something about compactness here, so really, if I'm completely honest, I should also say something about sort of the limits at S going to plus minus infinity. So, hooray, that is one sense of somewhere injectivity, and so this, from the overall picture, the story is done once I've found this sort of somewhere injective point, right? Because then I can make this all match up here. So we get back to all of that. So the note is that somehow the hard part, well, there are two hard parts here. Finding this P0 and finding that somewhere injectivity, which make the requirement of somewhere injectivity a little stronger. Usually. So, whoops la. Yeah. So, so what is the, I said we can wiggle with the S0 and T0, however, we'd better make sure that eta is still non-zero there. Right? So, eta is going to be non-zero on some open set, at least. So, that means since you don't have a choice of that open set, you'd better have a dense set of T's and S's, for which you can get your somewhere injectivity. Except if you also know unique continuation, right? So you can somehow replace this almost by something sort of minus what you get from unique continuation about the eta. So, there might be a unique continuation statement that says if eta is zero on an open set, it's actually zero everywhere. And that then means that I really just need to find some T0 and S0, because then eta cannot be zero on a neighborhood there.
Why do we have it like unique continuation for eta?
We may or may not. So this again goes back to.
Eta is just some arbitrary.
Well, eta satisfies an equation.
Oh, okay.
And again, that equation has a certain symmetry. That is actually, the same symmetry that we asked for in the beginning, right? And so there is also a unique continuation for eta that sort of comes exactly from the unique continuation for the. That comes exactly from the out orbits. Right. So on P1. The out orbit is everything, and so you actually sort of have unique continuation everywhere. So if you actually if your germ is zero at a point, you're zero everywhere. For the R action, you only have unique continuation in the R direction. So you need to be zero on an entire S1 orbit. That's wrong. The S1 is not the orbit, so you only have unique continuation along out orbits. So that means you actually just need to, you don't need almost, oh goodness, how does that, you don't need almost all T0s, oh goodness. Alright, so. Right, so. I would have, I mean, the simple thing would have been to say that for almost all T0s, S0, I have unique somewhere injectivity. And what this means here is I just need some T0 such that for almost all S0, I have unique continuation. And what that unique continuation means is, first of all, something that we usually need for this, and secondly, this injectivity that we had here. So that's somehow, yeah, the nonlinear injectivity. And if you write this out, what that is, at least in the Fleur example, and also in the in the just sort of holomorphic sphere example, you actually need the derivative of u, in transverse to the orbits. No, sorry, along the orbits, the orbit derivative of u to be non-zero. Which is something I haven't explained how that comes out here. So the reasoning here is somehow because this P0 on U is actually something that multiplies the DSU. Right, so if that's non-zero, there's no way I get that multiplication non-zero. Right. Hallelujah. So that is the meaning of somewhere injectivity is usually these two things. There's a sort of infinitesimal somewhere injectivity and a more global one. And in that sense, I can actually also say that I want this to be not equal to the limit when s goes to plus minus infinity in the Fleur case. So that's the meaning of somewhere injectivity. And the reason why we need somewhere injectivity to get equivariant transversality is exactly in this construction of making the linearized universal operator surjective, or proving that it is surjective. So that is the technical explanation for the bigger philosophy. Kind of depending on the symmetries that you have, you need more or less somewhere injectivity. Good. So that was about the red box, and the summary of this whole discussion is, well, if somebody tells you that they're going to do a geometric regularization of the moduli space, what are the questions you should ask them, and where should you really dig? So, first of all, discrete groups, you can go into orbifold world, so don't worry about those. When there's non-discrete groups, you really have to ask something. So a good starting point is what kind of perturbations you're using. And then once you're clear about that, the one technical question is, why is this linearized operator for the universal moduli space surjective? And the thing to watch out here for is the somewhere injectivity that you're probably going to need, which is sort of dual
Are there alternatives to summer injectivity?
Not for local things, right? Yeah. So there are sort of somewhat more non-local perturbations that I was hinting at when you let the J depend on where your curve intersects a certain hypersurface. Yeah, that was not covered by my way of writing it. Yeah. And then you kind of need less injectivity. Right? And right, so what we realized here is that really we would, we would like to make our perturbation depend more on our parameter in the base surface. Right? But not only does that break the symmetry that we're asking for, it might actually also cause other problems later on in the procedure, right? Because once we have these equivariant perturbations, we're going to still need a gluing theorem that's true. Right? And so if you just happen to make the J prime here depend on the base point, say in the sphere in P1, then, well, you would end up talking about broken curves here for a J prime that's also, varying with the base point on P1. And then you'd have to prove that this glued space here is actually compact. But when you go and look at sequences of J prime holomorphic curves and bubbling happens, the bubbled curve, just sees the J prime from the bubble point. And so it does not sit in this space, then, the bubble. Right? So that's one of the things that you sort of very subtle here that you should ask yourself whether that's, the way you perturb, whether that's still compatible with the compactness. So that's the two good questions to ask for geometric regularization. And next time we're going to start doing abstract regularizations, and there'll be essentially just 3 questions that I think sort of get us to all problems. Here, description is completely different, 0 set of some sections, so question is, what kind of section? And somehow what's most confusing in this is that people start to hand wave and say, oh, it's just like a section in finite dimensional bundles. But of course it's not. So there's fuzzy notation and fuzzy intuition. Can get in your way here. So you really forget about the idea that these are sections in finite dimensional vector bundles. And that's the same problem when you ask, why does this regularization theorem hold? Again, don't let yourself be fooled into believing everything by just analogy with the finite dimensional case. These will be much more complicated sections. But essentially all of these problems here are topological problems. So one, important things to look at when a regularization is things like Hausdorff property or compactness. But we're doing abstract perturbations here, so we're out of the world of Gromov compactness. So it's really just a sort of point set topological compactness that you need to preserve there. And the only place where you need to be worried about analysis is when you ask about somehow the second part of that whole program is, why is your pseudoholomorphic moduli space in fact of this form? So how do you find this section for a given, D-bar operator? And that's where the analysis comes in. So, yeah, we'll ask ourselves, these questions very separately, because I think that's, you tend to sort of always go back and forth between these arguments, of course, what kind of section do I get? Well, is that section good enough to have a regularization theorem? Yeah. But once there is a theory in front of you, it's really better to just separate things out. Because otherwise you tend to move problems from one to the other, and that can very easily be a cyclic argument. You get to problems here, you say, oh, well, I make the section here a little bit worse, and then you get to problems in the regularization theorem, and then you say, oh, well, let me assume some more good properties of the section, and then you get back here and you ask yourself, well, how do I prove those properties? And you might have forgotten that you were worried about those properties because of that, and then just decide to drop those properties again. So, separation of, what is that? Judge and state, it's the big thing. All right, and you get to ask me those questions all the time if that should ever not be clear. Of course, you get to ask me all questions.